Hello, I am recording the introduction to lab number 5, aspirin synthesis. So before I start explaining the lab, I wanted to just quickly go over the feedback survey that I shared with everyone today in the lab sessions. So I went through all of the responses. I had 52 out of 72 people respond. So that was 72.2% response rate. So the things that worked best um, were there were repeats. So I grouped them in together. So multiple people, said Lapster. So I just put it once. So the trends or the things that are working best for everyone's learning are the detailed notes, doing an introduction to lab. Some people liked the film labs and then others liked Labster labs. So there's a combination of both of them happening during the semester. They're both on the syllabus. So some weeks we'll do Labster, some weeks we'll watch a video on Jove and then do a worksheet, and other times we'll do the filmed lab. So tonight's lab is a little bit longer. It's a 27-minute video, so there's no extra worksheet or activity. The quiz is the only part of lab 5 that you'll submit, and it's a 10-point quiz and it's on to you. So after it closes today, I can reopen it for anyone that's making up tonight's lab. Excuse me. So a couple other things, giving correct answers to worksheets has been working well for everyone. Working independently. So some of the labs don't require any group work or breakout rooms, but if we do have a lab that I told this to the other students, but if there's ever a lab that you don't want to work in a breakout room, I know everyone has a lot of things going on, so you can not go into the breakout room and then just stay in the main room with me, and then I can guide you a little bit and you could work independently on the lab outside of Zoom if you want, or you can work in the main room, with your camera off or sound off, and I can be there to answer questions. Something I wanted to bring up was the lecture and lab topic. So when I designed the syllabus, I made sure that what you're learning in lecture is familiar in the lab. So for example, this week, there's some carboxylic acids and alcohols in tonight's lab, which you covered alcohols already in lecture, and this week you're talking about carboxylic acids. So I tried to line up all the labs with what you're learning in lecture. In lab, though, we do lab activities. So we talk about experiments or experiments pretty much, and organic chemistry experiments that you can run. So we aren't going to be doing problem solving like you would do in the lecture. So this lab is not going to be like what you're doing in lecture, but if you ever have a question that you're not sure about that you're talking about in lecture, I can try to help. And if you come to lab and wanted to talk about something you learned about carboxylic acids, for example, in lecture, and you wanted me to try to go over it, that's totally fine, and we can try to work on it in lab. But the lab is separate from lecture in that we won't spend our time problem solving in lab. We'll talk about an experiment or topics that are organic chemistry lab related. So also I'll do more PowerPoint slides, because that sounded like with some responses it was something people liked, and instead of doing a Word document, I can do some PowerPoint slides instead. Yeah, so those are the things that are working best for supporting learning. What can be improved? So if there's a question about longer quizzes, if we'll ever have a longer quiz, can we have more time and not having to submit it the same day? So we'll never have a longer quiz until we get to the final, which is a quiz, and it's a 25-point quiz. So that one's going to be timed because it is the final, but I'll do a practice final quiz with similar questions, and then you can practice taking the the final exam. So it's kind of like a run through, but the questions will be a little bit different, and then you can see how the timing goes, and if you're able to answer the questions in time. So I'm thinking either 10 questions, 2.5 points, or if I do more questions than that, then some of the questions will be worth less points. But all the other quizzes we're doing, since they're only short 10-point quizzes, 10 points or less, they'll just still be due the same day. But if you ever run into difficulty, you can't take the quiz that day, just email me and I can reopen it later. So there's also kind of a split. So some people want more labs for labs, and some people want more film labs. So I think as it is right now, it's a good split with the number of labs for labs to recorded labs. And that brings me to this question that I asked on the survey about, would we rather have a recorded experiment on YouTube or a labs for labs? So 57.7% wanted to do a recorded experiment on YouTube instead of a labster lab. So I'm thinking of replacing the carbohydrate lab at the end of the semester with a recorded experiment of some type of carbohydrate experiment. So that will be replacing one of those labster labs in the end, but during the semester, we're going to be doing a total of 4 labster labs. So there's still going to be labster labs. We've done one, we'll do one next week, and then there's 2 left at the end of the semester. So there's still opportunity to do labster labs. Picking your own groups. So that's something I'm gonna think about this week and how I can make that happen, since I don't know who knows who. So that's on my agenda. Less group work, more class activities. I'm going to try to think of a class activity instead of doing a breakout room activity at some point this semester. So we're only at lab 5, and there's, how many labs do we have left? I think there's 5 left at this point, right? Let's quickly check. Yeah, 10 labs. So we're halfway through. This is our 5th lab, and there's 5 more after this, and then lab 11 is our lab quiz. So those are all the points I wanted to go through. If there's ever any questions about quizzes or how you did on a quiz, just send me an email and we could talk about it. And then I'll try to do a little review at the beginning of the lab. So we had a quiz this week. Next week, I'll try to do a review, just so if anyone got a question wrong on the quiz, we can discuss the correct answer and why the correct answer was the correct answer. So I'll try to be doing that. Topics of interest: medications, food, diet, cosmetics, nutrition, vitamins, exercise science. So I'm going to try to include a real life topic for each lab. So this week I'll be talking about medication. So I'm synthesizing aspirin, which is a medication. I'll talk a little bit more about other medications. And then there was a couple comments about Zoom and Labster not working together. So when we're doing a Labster lab, you don't have to keep Zoom open and running. If it's slowing your computer down, you can just close out of Zoom and just have Labster running on your computer. And then just feel free to email me if you ever want to discuss your grades. And with grades that aren't reported in 2U, just the Labster grades go to 2U. So when you finish a Labster, it'll tell you what your grade was. And the lab 1, where it was in the Google Drive, I graded that. But last week, for example, when we did the group activity, everyone gets 20 points for the group activity, and I'll go through everyone's worksheet just to make sure the answers are correct, but you get 20 points for that. So the flexible points in last week's lab is the quiz that you did independently, which is 5 points. So if you got a 4 on the quiz last week, a 4 out of 5, your grade for last week's lab is going to be a 24 out of 25. So you get 20 automatically for working in your group, and then the 5 points is up to you. It was that independent quiz. So that's how grades for those type of labs work. In today's lab, it's worth 25 points and the quiz is worth 10. There's a question that's not worth any points on the quiz that just asks, did you watch the video? So then I know that you get the 15 points for watching the video, and then the extra 10 points for the quiz makes it 25 points for today's lab. So just if you ever have questions about what your grades are, just reach out to me because I keep them all in a log that I can tell you what your grade is. Okay, so that's the feedback survey. So this was the lab we did today, aspirin synthesis. So aspirin is one of the most widely used medications in the world. A lot of people take it for different reasons. Older people will take aspirin if they're prescribed by their doctor, if they have any risk of heart attack or stroke. Like if you've had a heart attack or stroke, you may be prescribed aspirin to prevent another one from happening. And it's because aspirin works to thin your blood. So heart attacks and strokes can be caused by clots in your body. And the aspirin, if you're taking aspirin daily, low dose aspirin, which is usually 81 milligrams, it helps to prevent those clots from forming, which can prevent another heart attack or stroke from happening. Some people who have atrial fibrillation, even if they're younger, someone my age I know who takes daily low dose aspirin, they have atrial fibrillation. So they take low dose aspirin to prevent a stroke from happening for them. So you don't have to be old just to take low dose aspirin. It just depends on your medical history, and it's something your doctor and you can discuss. So anyway, aspirin is an analgesic, which is another name for a pain reliever. It's also an antipyretic, which is a fever controller. And it was first isolated from the bark of willow trees. So it comes from the bark of a tree. And Hippocrates, I think is how you say it. He's considered the father of modern medicine. So in medical school, you learn about the Hippocratic Oath, which is do no harm, respect patient privacy, things like that. So this is back in, I think it's like the 4th century BC that he was around. So he would chew on this bark, and the bark contained salicylic acid, and it helped to alleviate pain. So the problem with salicylic acid is it can cause side effects. So some of the side effects are stomach pain, and that may cause ulcers in some people. So the reason why salicylic acid can cause those side effects is because it contains a carboxylic acid group, which is COOH, and you should be learning about that this week in lecture. And it also contains an alcohol that's bound to a benzene, which is a phenol. So here is the structure of salicylic acid. And I'm going to try this annotation here. So here we have our carboxylic acid. Right there, it's a C double bonded to an O, and then it has the alcohol group, so COOH is our carboxylic acid. And then the phenol group and salicylic acid is right here. So that's our phenol. Hard to write with this on a trackpad, so here we go. There's our phenol. So our salicylic acid contains carboxylic acid and a phenol. And when I move, this moves, unfortunately. So I'm gonna have to get rid of that. Okay, so our salicylic acid contains a carboxylic acid and an alcohol down to a benzene, so it contains a phenol and a carboxylic acid group. Phenols are very acidic. We talked about them a few labs ago when I was talking about that skincare product that was around in the 70s, and they stopped. Well, they still make it with the phenol, but they made a new version that doesn't contain phenol because it's a very strong acid and it was causing irritation on people's skin. So phenols are more acidic than other alcohols, and then combined with the carboxylic acid, it makes salicylic acid very acidic, and that can irritate your stomach because it brings the pH in your already very acidic stomach even lower, which can cause stomach pain and stomach upset. So chemists had to find a way to modify the salicylic acid and lower that acidity level so people wouldn't experience side effects and they could still alleviate pain with salicylic acid. So they started by doing this reaction here. So this is the reaction they did, but basically it's a carboxylic acid and an alcohol reacting with an acid catalyst. So an acid catalyst is a catalyst is something that speeds up a reaction. They use sulfuric acid here. So they take the carboxylic acid portion of the salicylic acid and the alcohol of acetic acid, and this forms an ester and a byproduct of water, which is pretty benign. The water doesn't do anything. It's just a byproduct of the reaction. So here is the reaction that they did. So we went from a phenol here trying to draw here. Here's our, start over. Here's our phenol and our carboxylic acid and acetic acid, which is a carboxylic acid as well, right? It has carboxylic acid there. So they're reacting it with their sulfuric acid, and it gives us this ester group, which forms here. So the ester group is here. Here's our ester. So it's your oxygen attached to an R group, which is the benzene ring, and it's attached to this other carbon here. So R, O, R is our ester. So an ester is much less acidic than everything that was on the salicylic acid. So the phenol is more acidic. The carboxylic acid is more acidic. So this ester that replaces the phenol group, even though our aspirin has a carboxylic acid, because we've gotten rid of our phenol and replaced it with an ester group, it makes it much less acidic. So the product that these chemists came up with was called acetylsalicylic acid, or aspirin, and it's abbreviated ASA. If you've ever worked in a hospital or healthcare setting, or maybe you've seen a family member's medical records, or maybe your own medical records, and you see ASA, that means acetylsalicylic acid, aka aspirin. So that is the reaction that these chemists came up with by reacting the phenol group with acetic acid and forming their aspirin, which is an ester group. So in today's experiment, I didn't use acetic acid, and I did not use sulfuric acid. I used acetic anhydride instead of acetic acid, and I used phosphoric acid instead of sulfuric acid. So phosphoric acid is still a strong acid, the same as sulfuric acid. It's still going to act as an acid catalyst. Acetic anhydride is a more efficient, it's more efficient to use than acetic acid, and it reacts more rapidly. So that's why I used acetic anhydride. And I'm still going to be reacting salicylic acid. I've just changed my acetic acid to acetic anhydride, and I've used phosphoric acid instead of sulfuric acid. So this change here gives me aspirin, just as above, but it also gives me a byproduct of acetic acid. So acetic acid is vinegar, pretty much. So it's also pretty benign, like water. It's just a byproduct, and it actually can be washed away if you purify your aspirin sample, which I'll talk about below. So the only purifying that I did just because of time was I washed my aspirin sample with water. And I did this to destroy any leftover acetic anhydride that was present in my mixture of salicylic acid and acetic anhydride with phosphoric acid. So the cold water that I used was to destroy the acetic anhydride, and also to help the aspirin solidify or crystallize is another word for that. And I use cold water because if you use warm water, it's going to dissolve your aspirin. So you use cold water to ensure that the aspirin stays solid. This was the step that I did not include in the experiment because it would take additional time. It's called recrystallization. So what I'm showing you in the experiment is I created my aspirin product and I vacuum filtered all of the liquid out of it. So just a solid remains. And then I rinsed it with cold water. Recrystallization would be a next step. So once I have my product, I would redo most of the steps that you'll have seen in the video. And I would take my aspirin that I just made, place it into a container and mix it with ethanol and heat it up. And then I would add a little bit of warm water to it. And I would dissolve all the crystals. So it's all dissolved together, the ethanol, water, and the aspirin crystals. Then I'd put it in an ice bath. I would stir it up and I would put it in my vacuum filtration and push air through it or suck the liquid out using air like a vacuum. And I would have just a solid aspirin product left. So the reason why recrystallization is important for making a pure product is because in a reaction you might have unreacted reactants. So in this experiment, you would have unreacted salicylic acid, which is one of the starting materials. So if that unreacted salicylic acid is present in your aspirin, salicylic acid is the thing that was causing stomach pain. So if there's salicylic acid in your aspirin, that's not a good thing because you made the aspirin to avoid any of those side effects from the salicylic acid. So unless I recrystallized my product, which I did not, there's going to be unreacted salicylic acid still there, and that'll give you a positive phenol test. So I do perform a phenol test in the experiment, and I find out that there is unreacted salicylic acid in there, which I expected because I did not do the recrystallization. So the phenol test is the same test that we did a couple labs ago, where I used it looked like orange juice or Sunny D, and I added it to a test tube, and the test tube contained a phenol, and the test tube changed to a purple color. So it's the same test. It's the ferric chloride test or the phenol test using ferric chloride. So in the experiment, I take a piece of filter paper and I put a drop of ferric chloride solution, which is orange, and then I added some of my dissolved aspirin to the spot. So I dissolved my aspirin in acetone, and then I added it to the spot of ferric chloride solution, and I found out that it turned purple. And so that means that my aspirin product, my synthesized aspirin, did contain phenols. So I know it contains salicylic acid because there's the phenol of the salicylic acid there. So it turned purple. So I knew that I didn't purify my sample completely. Recrystallization would have helped with that. So that's one reason for recrystallization. Acetic anhydride is used in excess. So basically that means that you're using more acetic anhydride than necessary to facilitate your reaction. And unless you recrystallize it with these steps, there's still going to be some left over after the initial reaction. And then phosphoric acid and acetic acid might also be present in levels that might not be safe. Even though acetic acid is pretty benign, it's just vinegar. If it's still not great because your product is not pure. It's not pure aspirin. And then the phosphoric acid is a strong acid, so That's not a good thing to have in your aspirin either. So all those reasons are why the recrystallization is important, and unfortunately they weren't included, but it's good to just know that there is a way to further purify aspirin products. So during that recrystallization, when the impure aspirin is dissolved in the hot ethanol and hot water, it's less soluble in a cold solvent than hot. So what that means is that it's less soluble in cold solvent, but more soluble in hot. So it's going to dissolve in the hot ethanol and water, and it's going to be less soluble in cold, meaning that it's going to solidify when it's cold versus the solvents. So the ethanol, the water, those are not going to dissolve. They're going to stay liquid. And the impurities in the aspirin, like the salicylic acid, the acetic anhydride, and the phosphoric acid, are all going to be left in the liquid solvent. And then your less soluble aspirin is going to harden into crystals or into a solid and leave all of the liquid byproducts behind. All those impurities are going to be left behind in the solvent. So then you would take the container and vacuum filter it again, just as I show in the video. And then after this recrystallization step, all of those impurities are going to get drained away, and then you're left with just your solid aspirin crystals, free from salicylic acid, free from acetic anhydride, acetic acid, and phosphoric acid. So I wrote here, since I did not recrystallize my aspirin, there's going to be impurities present, and I test that using the ferric chloride test for phenols, and I found out that there is unreacted salicylic acid in my synthesized aspirin, and it turned a purple color. There's a question on the quiz: what's an ideal test result for synthesized aspirin with the phenol test or the ferric chloride test? An ideal result would be no change. You don't want to see the purple change. So you would want no change. You would want the spot that you're looking at to remain its orange color, the orange color ferric chloride. If it turns purple, that's not ideal. That's not an ideal result, because that means that your aspirin's impure and it's not safe. So an ideal would be no impurities, no salicylic acid, and a negative test for a phenol test. And I also wrote down here at the bottom, these are just some notes that are at the bottom of the procedures. So I go through these procedures in the video, but I don't think I didn't address this because I added this last minute. So my synthesized aspirin was positive for phenols, which means that salicylic acid was present. You'll see that I run a TLC plate using my synthesized aspirin and just a crushed aspirin tablet from the pharmacy. And my spots they were identical on the plates. They had the same RF. My plates didn't look great, and I go through at the very end of the video why that might have happened. But the solvent front, it was the solvent front that didn't look good. It was very smudged and it had a zigzag line, and normally you don't see that zigzag line. But I talk about the reason why there. So my spots look the same, and normally if you spot a TLC plate with aspirin that's impure, you're going to see multiple spots, but I did not see multiple spots on the plate. I just saw one spot for my synthesized aspirin, and then the same height of a spot for my crushed aspirin tablet. So the reason why is TLC is kind of limiting. It's a very simple experiment. It doesn't really tell you too much about purity. So my synthesized aspirin could have contained enough aspirin, pure aspirin, to give me the same result as a regular aspirin tablet on TLC. If I ran more advanced testing, like in a lab setting, if I ran something called HPLC or like NMR, something that's in a more advanced chemistry lab, I would be able to test my synthesized aspirin a little bit better and see if it was impure. But try not to get confused about the phenol test being positive and then the TLC looking normal, because TLC is such a limiting test. It can only tell you so much. So my product was impure, but according to my TLC, it had the same RF as aspirin, and it's just because the nature of TLC. So these are just some descriptions about the labs and how the points are going to work for the lab. So let's say you get an 8 out of 10 on the quiz. Your final score for the lab is going to be a 23 out of 25, so minus 2 points. Because you get 15 points for watching the video, and there's a question on the quiz, it's not given any points, but it just says, I attest that I watched the video, so I know that the 15 points you get for the video, and then the other 10 points is the actual graded quiz. So if you get 1 point off your quiz, you get a 9 out of 10, it's a 24 out of 25. And last thing I wanted to go over was this that I added in red. So these are points that'll help with the quiz. Since I couldn't make a quiz just all about aspirin, there's really not that many quiz questions you can use about aspirin. So I did put some additional TLC questions there because I did run a TLC today. So the lower your RF, so remember the RF is the distance, I'll write it here, RF equals the distance your spot travels, and then that's over that's in centimeters, over the distance the solvent travels. So if you have an RF of like a very low RF of like 0.1, that means that your spot did not move very far at all. But if you had an RF of like 0.8, that spot moved much farther up the plate. I think in the video, my RF of both my synthesized aspirin and regular aspirin was like 0.81, which is pretty high. So you'll see that it's like just below the solvent line. It went up very high. So the lower the RF, the less far your spot travels. And that's because the spot wants to stay where it is, and it wants to stay on the silica plate. So if it has a lower RF, it's on the bottom of the plate. It's very attracted to the polar stationary phase, which is the silica gel coated plate. And that means that it's more polar. So here's your TLC plate, and your spot is like right there at the bottom. That means it really wants to hold on tightly to the silica gel, and it doesn't want to move because it is more polar. If you have a spot that's further up, that means that it doesn't want to hold on to the silica gel. It just moves up, and it moves with your more non-polar solvent. So the non-polar solvent is working its way up, and it's taking that other spot all the way up to whatever point, maybe 0.8. So the lower the RF, the more polar your compound is. So why I wash the aspirin with cold water is also another question on the quiz. I washed it with cold water in the video because I didn't want to dissolve any of the aspirin. If I used warm or room temperature water and poured it over my aspirin, I would have dissolved some of it, and then I wouldn't have enough product to test on the TLC plate and also perform a phenol test on. And then last thing I wanted to cover was the ferric chloride test it turns purple for phenols. I would ideally not want to see a purple result because that means that there's unreacted salicylic acid in my synthesized aspirin. So in an ideal world, if I did everything correctly and I was able to recrystallize my aspirin, I would test it for phenols and it would not change. So I would just see that orange color. I would have an orange dot and I would apply my synthesized aspirin and it would stay orange. The not ideal is what you see in the video where it turns purple, because that means that it's not pure. It's the contaminant of the salicylic acid, which I don't want in my aspirin. I want to avoid having salicylic acid in my aspirin. So those will help with the quiz questions, and that is all for this lab. And I hope it goes well, and I will see you next week.